In this video, I want to really just use these two equations, r equals 3 and r equals 2 sine theta plus 3, to do a lot of different shapes and show you a lot of different things we could do. So I'm going to start with shading a region I want to find the area of. So let's start with this. Let's start by shading this region, and let's try and find the area of that. Okay, so the circle, of course, is r equals 3. The cardioid, or the dimpled limacon, r equals 2 sine theta plus 3 up here. Always good idea to know where they intersect. And you know, this one is right on the axis, so I think we can probably make a pretty good guess about it. But remember, I always like to draw a line from the origin to the intersection points. It helps me to kind of see where each function is kind of the actual function we're finding the area of. Okay? So I'm going to start by setting the two equations equal to each other, because it's just always helpful to know exactly where do they intersect. So if I subtract 3 from both sides, divide by 2, I'm looking for where sine is 0. Sine is 0 at both 0 and pi, which I think, judging by the graph, is what we would have expected. Okay? So I want to find the area from 0 to pi of the limacon, and then I'm going to find the area from 0 to pi of the circle, and I'm going to then subtract the two areas. Now, because these two things are going to have the same bounds, they're both going to be 0 to pi, you actually could put them together into one integral. I often don't in polar, just because it's not always a given that the bounds are going to be the same, and I kind of like to keep these things separate. So let me maybe color code this a little bit. What I'm finding right here, 1/2 the integral from 0 to pi, this is this region right here. That's what I found with that integral. Okay, 1/2 the integral from 0 to pi of just 3. That gives me this area right there. So if I subtract the 2, that will give me the area that I originally wanted, that red shaded area. Let's look at another area. In this one, let's do, instead, let's do this area down here. Okay. So the intersection points didn't change. It's still pi and 0. Okay. I think the best bet now is to find the area of the circle and then find the area of the limacon and subtract. And again, I'm going to color code this as best I can, and we're going to need to talk about the bounds a little bit. Let's start with the circle. 1/2 the integral of 3 squared d theta. Okay. Now, getting to the bounds, where we want to start this integral is at pi, right? We want to sweep through from pi. So we start at pi. Now, the problem with this is, and the thing to be careful of, is we can't say 0, right? You can't go from pi to 0. Number one, you learned in Calc 1 when we were just dealing with x's that you don't like to go in your bounds from small to big. You get the opposite of the answer. But in fact, if you go from pi to 0, you're going to track this way. Well, it doesn't make a huge difference in polar, but of course, if we're doing the limacon, if we went from pi to 0, instead of getting the shape down here that we want, we would go this way. So we have to be really careful. In polar, it is vital that the bounds go in the correct order, meaning smallest to biggest. So instead of 0, you know what? Let's just call it 2 pi, right? That'll keep the order. So there we are. Now let me write down what we just found. We just found that area in black. Okay. Next, I want to find the area, this right here, of the limacon. So I'm going to have 1/2 the integral from pi to to 2 pi of 2 sine theta plus 3 squared d theta. And I should just be able to subtract them. And again, that will give me the red area that I want. So make sure you are getting the bounds in the correct order. Again, let me explain real quick why pi to 0 wouldn't work. Number one, it's in Calc 1, when we're talking about dx or dy, if the bounds are in the wrong order, you get the opposite of the right answer. Well, it's more of a problem in polar coordinates. Because let's look at the limacon. If you went from 0 to, or from pi to 0, you wouldn't be tracking what you want. You'd be going from pi around to 0 this way. Well, that's totally the wrong part of the shape. So you really have to make sure the bounds are right. Let's look at one more. In this one, I'm going to, I want to find this area right here. I want to find the area that's shared by the two. Okay. Well, again, these didn't change. Still pi, still 0. Or in this case, I think you could, I'm going to put like or 2 pi. So I don't think there's a nice way here to do anything with subtraction. I mean, I guess you could find the shapes and kind of from 0 to pi and from pi to 2 pi, the huge shapes, and do something. But I think the easiest way here will actually be to do this and add two pieces together. So let me explain that. I'm going to start with 1/2 the integral from 0 to pi of r of just 3 squared d theta. And let me shade in what that just found. That just found this area right here. Give me the circle, the top of my shape. Well then, if I turn around and I do the integral from pi to 2 pi of the limacon, I get this. Well, then all I should need to do is add the two together, and I've got the shape I want. So there are lots of things that can be done, and different shapes that can be, you can find the area of all with the same equations. It's just a matter of really being careful of tracking, what exactly is being drawn. And I always go back to a windshield wiper. It's a helpful way to think about it. When you go from 0 to pi, you're sweeping through this way. So like r equals 3, as you go from 0 to pi, you sweep through like a windshield wiper, and all of this gets covered. And then you go from pi to 2 pi, you sweep through from there, and all of this gets covered in that shape. So maybe helpful to think about. Just be real careful, find the bounds, and then, it's always helpful to draw lines from the origin out. It's always helpful to actually do some shading on the graph. So just be careful with bounds.